Okay, Calculus 3 students, this is most likely going to be my last video lecture for this course. Remember, this is an asynchronous course. When this course was set up by the math department at Oakton College, it was set up as an asynchronous course. So what is an asynchronous online course? There are two types of online courses, asynchronous and synchronous. Synchronous online courses are courses where everyone gets together at the same time to watch the professor deliver a lecture using Big Blue Button or Zoom or some other, video conferencing software tool. Okay, that's a synchronous course. Asynchronous is where you do the work on your own and you email the professor or you request a private video conference with your professor if you feel that you need extra help or extra assistance. This course was never meant to be synchronous. It is an asynchronous course. That's how the course was set up. So if I don't deliver regular video lectures, it's not because, oh, Mr. Lewitt is lazy, he doesn't like to lecture, No, this course was set up to be asynchronous from the very first day. So again, just so that we're clear about this is an asynchronous course, which means that students work independently and then email me or request a private video conference if they feel they need the extra help. Okay, so technically, I'm not even required by the department to provide you with video lectures. I do it because I think it's a really good idea, and I think it will help at least some of you, maybe even all of you. Okay? But I think, some people in the class might be a little bit unclear about the nature of this course. Okay? So, I want to make that very, very clear. And that's something that you should know. There is a big difference between an asynchronous course, an asynchronous online course, versus a synchronous online course. They are very different. They are very different. An asynchronous course is like, basically an independent study. It's really what it is. Okay, so I just want to be very clear about that because I think, some people in the class sort of have this attitude, oh, Mr. Lewitt doesn't like to teach, whatever. Well, that's not really true. Okay, all right, so enough preaching, although that was important. That was very important. Enough preaching, let's get to some homework. This is your last homework assignment, all right? This is your last homework assignment. Excuse me. Okay. So, problem number 1, write an iterated integral that gives the volume of the solid bounded by the surface f of x and y is equal to x times y over the square. R is made up of the points x and y such that x falls between 1 and 5 and y falls between 3 and 6. So we have choices here. So x goes from, okay, it's not going to be a, okay, because the x limits are 1 to 5, and here we see that the y limits are 1 to 5. So that's not going to work. I think it might be B. Let me take a look more carefully. the x limits are 1 to 5, and the y limits are 6 to 3. No, that's going to be a problem. 3 should be on the bottom and 6 should be on the top. Okay, I believe it's going to be option D. So okay, 1 second. We have this integral right over here. So we have the integrand, which is x times y, and we're integrating with respect to x. The limits of x are 1 to 5. And then when we're done with that integration, we have to integrate again with respect to y. Okay. And those limits are 3 to 6. 3 on the bottom, 6 on the top. Okay, so it should be D. Okay? Hold on 1 second. I just want to wipe some dirt off my computer. There we go. All right. So let's move on and do another homework problem. This one should be very easy. Okay. Problem number 2. Consider the integral. Give the variable of integration in the first or inner integral and the limits of integration. Give the variable of integration in the second or outer integral and the limits of integration. Well, pretty easy. It's a simple problem like the first one. The variable of integration in the first or inner integral is y. The lower limit of integration is -3. And the upper limit of integration is 4. The variable of integration in the second or outer integral is x. And the lower limit of integration is 0 and 5. And by the way, these can be reversed. I hope you understand that. These can be reversed, but of course, if you reverse the order of dy and dx, you also must reverse these limits as well. Okay, so for example, what I would end up with is, let me see, 2y squared plus xy. I'm going to reverse the dy and dx. We'll have dx and dy. But if I reverse dy dx and write down dx dy, these must also be reversed. 0, 5, -3, and 4. Okay? Because otherwise I'm going to have a different answer because it's a different multiple integral. Okay? And that should be correct. Okay, so we have to evaluate the following iterated integral. An iterated integral is the same as a multiple integral. Okay, so we can use Mathematica. Sometimes it's good to do these things by hand. So I have 4xy integrate with respect to x. Okay, so my variable of integration is actually x. So what I could write is 4y. 4y is like a constant. X dx. And that's going to be equal to 4y times x squared over 2. And we don't have to worry about the plus c because this is a definite integral with real numerical limits, so 0, 3. Okay, and then we simply evaluate it, so we're going to have, well, this is going to be, if x is 0, we have 0 squared is 0 divided by 2 is 0, and 4y times 0 is just 0. So we don't even have to worry about that. Let's just worry about the 3. So we're going to have 4 times y times 3 squared is 9. 9 divided by 2. And that's equal to, let's see, 2, okay, 2 cancels out. 2 into 4 is 2. And then we have 2y times 9. We have 18y. We have 18y. Okay, let's see, I need more space to write. Okay, so, okay, that was, let me write this, okay, the previous answer was 18y. Okay, so I look at the outermost integral. I have 0, that's a lower limit. 2 is my upper limit. I have 18y. And I'm integrating with respect to dy. Okay, again, very easy. That's simply going to be 18 y squared over 2. And that's going to simplify to 9 y squared. Okay, and again, so it's actually, okay, I need more space for writing. When I do the evaluation, I'm going to have 9 times 2 squared minus 9 times 0 squared. But 9 times 0 squared, we don't have to worry about this. This is just going to be 0. So this part evaluates to 4. So we have 9 times 4. What is that equal to? That's going to be equal to 36. Okay, so that's equal to 36. So let's just ignore the dog for right now. He's only 20 pounds, but he has a very strong bark. A very strong bark. Okay, so the answer is 36. Chachki, quiet. Okay, the answer is 36. Okay, the answer is 36. And let's see if that's the correct answer. Okay, now let me show you something, guys. How would you do this in Mathematica? It's pretty, whoop, 1 second here. Oh my God, what's going on here? How would I do this? Okay, how would I do this in Mathematica? So there are a couple of different ways that you can do this in Mathematica. Integrate, 4 times x times y. The x limits go from 0 to 3. The y limits go from 0 to 2. Okay, that's one way of doing it. The other way of doing it is escape dintT, escape. And then here inside, the integrand, okay, the inner part of the integral, the inner part of the definite integral, we're going to repeat the process. dintT, okay, and then escape again. I recommend using parentheses. 4 times x times y. My inner variable of integration is x. My outer variable of integration is y. My x limits are 0 to 3. My y limits are 0 to 2. Oops, wait a minute. Hey, 0, let me get rid of that 0 over there. Okay, there we go. And shift enter. Okay, so there are 2 different ways of figuring this out. There are 2 different ways of figuring this out. Okay, personally, my personal opinion is I like to do it this way better because it's just easier to type. It's easier to type. But this way has the advantage of looking like the iterated integrals in your homework assignment. So this way is kind of cool because it looks like a math problem from, a calculus textbook. So from that point of view, this has the advantage. I prefer doing it this way because I think it's faster to type. It's faster to type it out. Okay, so, use whichever approach is going to work for you because everyone's mind is a little different. Different people learn in different ways. Different people learn in different ways. So that's kind of important to remember, okay? Let's see what else. We have a lot of interesting problems in this homework. Okay, this is very similar to the previous problem. Okay, so some of these can get really tricky. Okay, 1 second. I think I saw a problem in your homework last night. It's sort of like problem 9, but it's a little bit, it lends itself better to this video because I can really help you visualize it a little better. Let me jump over to problem 26. I looked at this problem last night, so this is really, really interesting. It's interesting for a lot of reasons. Let me take a quick drink of water, guys. 1 second. Okay. When you change the order of integration, you have to be really careful because it will change the limits. Now, if you're integrating over a rectangular region in R2, then, changing the limits is actually pretty easy. But if you're integrating over a non-rectangular region of R2, then the situation becomes a lot more complex, all right? Then it becomes a lot more complex. So I really want to demonstrate that. I want to demonstrate that with this particular problem. So we have a region bounded by the triangle with vertices 0, 0, 8, 0, and 4, 1. Write a single iterated integral of a continuous function f over the following region. Okay. So I want to draw the triangle. List plot 0, 0, 8, 0, and 4, 1. Plot markers, filled circle, close the bracket. I'll make it 20 pixels across, 20 pixels in diameter. Excuse me. Plot style, let's say blue, and joined false. Okay, so that's what the triangle looks like. The problem is these points are getting cut off at the bottom, so we can change that. Plot range x will go from, let's say, -1 to 9, and y will go from -0.2 to 1.2, and that should give us enough space to see the circles a little better. Much nicer. Okay. So now at least, you know, we can visualize what's going on, right? We can see the problem a little bit better. Excuse me, I have a little bit of a sore throat this morning. Okay. So now we can see the triangle. So I want to connect these dots. So first of all, we can draw the line along the bottom. That's pretty easy. That's just y is equal to 0. X goes from 0 to 8. Plot style. Absolute thickness, let's say 4. Black. And remember, guys, if you're combining 2 or more pictures, everything has to be encased within the show command or show function. So now we see the line at the bottom. We see the line at the bottom of the triangle. Okay, terrific. Now don't forget, we also have the line over here. Okay, we have a line going from 0, 0 to 8. Oh, sorry, this is the line from 0, 0 to 8, 0. And don't forget, we have the line that goes from 0, 0 to 4, 1. So we have the line determined by these 2 points, and we have the line determined by these 2 points. Okay. So if we're going here, we have the line 0, 0, right? And 4, 1. Okay. So then we have 1 minus 0 divided by 4 minus 0. Okay. Which gives us a slope of 1 over 4. So we're going to have y is equal to 1 over 4, oops, sorry about that, 1 over 4x plus b. Okay. Well, we can see right over here, you know, what happens so what happens if you have 0, 0? Well, 1/4 times 0 is equal to 0. And if you have 4, 1/4 times 4 is equal to 1, which means we don't even have to worry about b, because for this problem, b is going to be equal to 0. So that's pretty easy. So then right over here, we have plot 1/4 times x, where x goes from 0 to 4, 0 to 4, and the plot style is absolute thickness for black. Okay. So that looks pretty good. Now what about this line right over here? So we can see that there's a line segment that goes from 4, 1 to 8, 0. 4, 1, it goes from the point 4, 1, because we can see this is 4, 1, x is 4, y is 1, and this is the point x is 8, y is 0. So what's the slope? Well, 1 minus 0 is 1. 4 minus 8. So we have negative 1 over 4, which it's very similar to what we had last time. Okay. So we have y is equal to negative 1 over 4 x plus b. Now what happens when x is 4? So what happens when x is 4, and of course y is supposed to be 1? So we're going to have negative 1/4 times 4, and this is negative 1. Okay, and we know that negative 1 plus 2 gives me 1, which means the equation of that line is going to be y is equal to 2 minus 1/4 x, which is simply the same thing as x over 4. Okay? Oops, what did I just do? Okay, hold on a second. Okay. There we go. Okay. Plot 2 minus x over 4. X goes from 4 to 8. Plot style, absolute thickness for black. And we have to show all of these pictures together. Okay, so this looks pretty good. This should help you visualize the space. Okay, it should help you visualize the shape. Okay, so we are we're integrating a function of two variables over this particular space in R2. Okay, so this picture should help you to visualize what we're talking about. So let's make this just a little bit bigger. Image size 500 pixels across. Okay, so this is the line. Y is equal to 1/4 x. Okay, and this is the line y is equal to 2 minus x divided by 4. Now, there are different ways of thinking about this problem. If I was going to do this problem, what I would actually do is split this up into two separate integrals, two separate iterated integrals. Okay? However, that's not what they want you to do for this problem. Okay? That is, wait a second. There we go. That's not what they want you, hold on one second. That's not what they want you to do for this problem. They want a single integral. So we don't have the option of splitting this up. Like me personally, I would split this up into two different iterated integrals because it's just easier for me to think about it that way. They want you to do it, as a single iterated integral. So in order to do that, we have to really think carefully. We're basically integrating in this direction initially. We're integrating in this direction initially. And notice that I'm taking slices that are parallel to the x-axis, which means that my inner integral has to be evaluated with respect to x. Okay, which means that I don't want dy dx, I want dx dy. So let me repeat myself, because maybe some people didn't get it. Notice that I am taking strips or lines that are parallel to the x-axis. This is x and this is y. So I'm taking strips or lines that are parallel to the x-axis, which means that my inner integral has to be in terms of the variable x. So what that means is these equations have to be solved for x, actually. So, okay, and again, I'm kind of running out of room here to write. This would be a lot easier on a whiteboard. This becomes, if I multiply both sides by 4, I'm going to have x is equal to 4y. Here, okay, I'm going to have, well, this is getting very messy. I have y minus 2 is equal to negative x over 4. Okay, so then I have 2 minus y is equal to x over 4. Okay. And then I have here, finally, I have x is equal to 4 times 2 minus 4y. So this is going to be 8. 4 times 2, yeah, in parentheses. This has to be in parentheses, right? So 4 times 2 is 8 minus 4y. Minus 4y. Which means that my lower, so I'm integrating with respect to x, and the lower limit is going to be 4y, and then the upper limit is going to be 8 minus 4y. So notice that my x limits are being defined in terms of y. Notice now the y limits. The y limits are very, very simple. Y simply goes from 0 to 1. How do I know that? Well, look at the picture. Look at the picture. Right over here. Look at the picture. The upper limit of y is 1 and the lower limit is 0. very easy to, wait a minute, very easy to figure that out. So my my lower limit has to be 0, and my upper limit has to be 1. Now let's see if that's correct. 1 second. Okay. And again, there is another way of doing this problem. You could, hold on 1 second. You could actually split this up into 2 separate iterated integrals. So what am I talking about? So here you would say, let me see here, hold on. Okay, f of x and y. Hold on 1 second, and then you, okay, first I would have dy and then dx. Okay. And then, well, actually, here, this is doing it this way is extremely tedious. 1 second. So let me start over. Okay, so if I split this up into 2 iterated integrals, then what I really have up here, I would have x ranges. Okay, notice my strips now, my lines or my strips are actually parallel to the y-axis. Okay, so in this particular case, oh, that's not, hold on 1 second. Here, 1 second. So let me write it like this. It might be a little bit easier. Okay. F of x and, actually, let's use Mathematica notation. F of x and y. So here they did dx dy. I'm going to reverse that and do dy dx. dy dx plus, I'm going to copy and paste. Okay, that didn't work too well. Hold on 1 second. Hold on 1 second. Let me try this one more time. Let's actually use an example. So here it just tells you f of x and y. We'll say f of x and y is x times y. Okay, so we'll just say f of x and y is x times y. X times y. And then here for this problem, they're integrating first with respect to x and then with respect to y. We're going to integrate first with respect to y and then with respect to x. So here I'm going to have y and x. Okay, and just think about dividing this triangle into 2 parts. So this was the line y is equal to, 1 second, this was the line y is equal to 1/4 x. 1 second, and this was the line y is equal to 2 minus x over 4. Okay, let me just make sure we're okay there. Yeah, 2 minus x over 4 and 1/4 x. Okay. So what I can do over here is I could simply say for the left triangle, y goes from 0 to 1/4 x, or x over 4. Okay. And my x limit, sorry, my x limits, plural, my x limits, so I'm integrating with respect to y, so y goes from 0 to x over 4. Oh, those are the y limits, sorry, and then the x limits will go from 0 to 4. Plus, now I have to take care of the right side of the triangle. Okay. Let's do that again. Yx. Here, my x limits, the x limits go from 4 to 8. 4 to 8. And my y limits go from 0 up to 2 minus x over 4. And again, we're integrating over, we're integrating the function x times y. This is just an example. I'm using a specific example of f of x and y. What does this actually evaluate to? 16 over 3. Now, what if we do it the way that they did it, in your homework assignment? Let me just erase this. So in your homework assignment, and remember, guys, I'm using x times y instead of the generic f of x and y. So f of x and y is generic. It's any function f, right? It's any function of two variables, actually. So I'm replacing f of x and y with a very specific example. I'm using x times y. Okay, but it really doesn't matter what function you use as long as it's continuous over this triangular region. If it's not continuous, then you have a problem. Okay, let's try the integral. Oops. 1 second. Let me get that back. Let me narrow down my window a little bit. Okay. So here we have a single iterated integral instead of the sum of two iterated integrals. I'm using x times y as my specific example of f of x and y. I'm integrating first with respect to x, and then I'm integrating with respect to y. My x limits are 4y up to 8, 1 second. 8 minus 4y. My y limits are 0 to 1. And I should have the same answer, which is 16/3. So notice that there were two different ways of solving this problem depending on whether you integrate with respect to y first and then x, or do you want to integrate with respect to x first and then with respect to y? Now, personally, for a problem like this, the way that my brain visualizes this problem, I actually prefer this approach. It may look like more work, but it's just easier for me to visualize. It's easier for me to visualize the problem if I use this approach. But this other approach actually works just as well. It works just as well, and perhaps it's less work because you have a single iterated integral instead of the sum of two iterated integrals. But again, it really depends on how you visualize the problem. Okay, it really depends on how you visualize the problem. Okay, let's continue with some further examples. Okay. 27 looks interesting. Okay, 27 looks like an interesting problem. This is sort of the reverse of what we just did. 27 reads, sketch the region of integration and evaluate the following integral where r is bounded by y is equal to the absolute value of x and y is equal to 2. So the integrand in question is 6x plus y. And we're integrating over this particular area. Now we have to decide, or 1 second, we have to decide which graph is correct. Okay, well the absolute value function, guys, I mean, this one's actually pretty easy to figure out because we all know what the absolute value function looks like. The absolute value function looks like this, okay? The graph in the graph that we see in option C, and then we have the line y is equal to 2, which is right over here. So that's pretty easy to figure out. It has to be choice C. Okay, now all of this is well and good, but again, you have to be really careful with your limits of integration. So this is what I'm going to do. Let's actually do the graph in Mathematica. So we can see, well, let's just do the graph in Mathematica, okay? Or you can do the graph with pencil and paper, you know, on a sheet of paper if that makes you happier, but I prefer to use Mathematica, okay? So the first thing I'm going to do is plot the absolute value of x. X goes from -3 to 3. Plot style. Absolute thickness, I like 4 or 5. Make it black. Okay, that's what that picture looks like. It looks good. Now we want the line y is equal to 2. Plot 2. X goes from -3 to 3. Plot style. Absolute thickness 4. And then black. Of course, remember, we're combining 2 or more pictures, which means you must use the show function. Okay, that looks terrific. So now we have to get the region. We want to get this region, and for something like that, the best thing to use is probably region plot. Region plot. Region plot. Let's see. Now let's think about what we have to do. Y is greater than or equal to the absolute value of x. This is the absolute value of x, so we're looking for y values that are greater than the absolute value of x. And y has to be less than or equal to 2. X goes from -3 to 3, and y goes from, obviously, 0 to 2. Okay, and plot style, gray level 0.5 is just going to look very gray. And there we go. Okay. We could make that, kind of transparent. Opacity 0.5. Well, personally, I don't think it looks as good, but okay. So this is the picture in Mathematica. And you know what they say, a picture is worth 1,000 words. If you can visualize the problem, then you are more likely to understand the problem and be able to solve the problem, or at least figure out a strategy for solving the problem, okay? So how do we figure this out? Well, let's see. What are the y limits? On the bottom, we have the absolute value of x. So that's y is equal to the absolute value of x, and that's on the bottom. On the top, we have y is equal to 2. Y is equal to 2. Now, where do they intersect? Obviously, they're going to intersect right over here when x is 2 and y is 2. And here, the same thing. We have another point of intersection when x is negative 2 and y is 2. Okay, and then this, of course, is the point 0, 0. Okay, so this is how I'm thinking about the problem. We're going to start integrating in this direction. Okay, I'm integrating from absolute value of x. Y is equal to the absolute value of x from y is equal to 2. And then, of course, well, if you look at the lines, my strips or the lines that I'm drawing are parallel to the y-axis, which means that initially I am integrating with respect to y, and then after that I'm integrating with respect to x. So what am I going to do to set up this problem? How am I going to set up this problem? Okay, so I'm going to have to erase this, guys. I don't have a choice. I just don't have the room. So, okay. So to set up this problem, just like before, create my definite integral. And of course, I have an iterated integral. Okay. So initially, we are integrating with respect to y. And then on the outside, we're integrating with respect to x. And the function is 6x plus y. The function is 6x plus y. And I strongly recommend that you use parentheses. Okay. What are my y limits? At the bottom, I have y is equal to the absolute value of x. That's the bottom portion. And then on top, I have y is equal to 2. What about x? Well, it's easy. The x limits are from negative 2 to positive 2. Negative 2 to positive 2. Oh. Okay. So what is that answer going to be? Shift enter. Okay, the people who wrote this homework assignment, they really like that number 16 over 3. Isn't that what we had the last time? Or was that a little bit different? No, 16 over 3. So I guess the people who write these homework problems really like math problems where the answer is 16 over 3. Okay, so this is going to simply be 16 over 3. And let's see if Pearson accepts that. 1 second. Okay. So let's move a little deeper into the homework. Okay, this is really similar to what we just did. I would like to do I'd like to do one problem where we have to do an iterated integral in polar coordinates, and then we should do a line integral. The line integrals look hard, but they're really not that difficult. Let me see. Um, okay, let's try number 43. And then we're going to do a line integral. And then, guys, I think that's going to be it for this video because this video is going to start getting very, very long. Okay. Problem number 43. Find the volume V of the solid below the hyperboloid z is equal to 6 minus the square root of 1 plus x squared plus y squared and above the following region. So here we're in polar coordinates this time. We're not in rectangular or Cartesian coordinates. Now we're in a different coordinate system. So things are a little bit different. Not that terribly different, but just a little bit different. So here we are integrating over the circle that goes from theta. Theta goes from 0 to 2 pi. That's a complete circle. And the radius goes from 2 times the square root of 2 to the square root of 15. So this is like a donut. This is basically a donut. Okay. Set up the double integral in polar coordinates that is used to find the volume. Okay, so for this problem, this is a little bit tricky. So here we have to remember, here, let me turn on my pen. Here we have to remember that r is equal to, well, r squared actually is equal to x squared plus y squared if, we're converting from Cartesian coordinates to polar coordinates, okay? So this right over here is going to get changed to r squared, okay? So we're going to have 1 minus r squared, and then of course, 6 minus the square root, okay? So here, 1 second. Okay. So really this integral shouldn't be that difficult to set up because we're simply going to have, okay, once again, we're going to have an iterated integral. And first we're integrating with respect to r. And then we're integrating with respect to theta, escape, theta, escape. And my r limits are 2, square root of 2. And the upper limit, okay, that's the square root of 15. And my theta limits 0 to 2 pi, which is very typical. Those are oftentimes the limits for theta, because that's a complete circular revolution, 2 times pi. Okay. Now this part you have to be really tricky with. So we have 6 minus the square root of 1 plus r to the power of 2. And you might think this is the answer. This is actually not enough, because whenever you're integrating in polar coordinates, whenever you convert a function like this, a function of x and y, into a function of r and theta, it's important to multiply the entire function by r. Okay? If you want to find out the theory behind it, if you want to learn the reason why you're supposed to do that, I strongly encourage you to read your textbook, specifically the chapter in your textbook that deals with multiple integration, because I'm pretty sure the book contains a detailed explanation of why you're supposed to do that. I'm not going to explain that in the video because it's going to take too much time. But you need to multiply this entire thing by r. R times that whole thing. And actually, you need to enclose the entire thing in parentheses, because otherwise I don't think you're going to have the right answer. Okay, so it's r times 6 minus the square root of 1 plus r squared. And then when you're doing this in Mathematica, you should really enclose the entire integrand in parentheses. Okay, Shift Enter. The answer should be, oh, well, they're not looking for an answer yet. R square root 6, oh, wait a minute, sorry. R times 6 minus the square root of 1 plus r squared. Okay. And let's see, 2 times the square root of 2, the square root of 15, 0, and this is 2 times pi. 2 times pi. And that should be okay. Okay, and the volume, the volume should be 52 over 3. Oh, sorry, 52 pi over 3. Okay, 1 second. 52 pi over 3 cubic units. Cubic units, and that should be correct. Okay, what I'm going to have to do, guys, I'm getting a little burned out, so I need to get some things done. So I'm going to have to make a separate lecture, a separate video lecture on line integrals. I believe, okay, so there are 100 problems in this homework assignment. I believe that your line integrals actually begin after problem 60, or after problem 59. After problem 59 or after problem 60, that is when you have to do line integrals. Okay? So from problems 1 to 60, those are the problems from the first section of this chapter. And then line integrals are the subject of the second section of the chapter. And those homework problems, I believe, are from 60 or 61 to 100. I am going to have to do a separate video on that. That's it's really not that horrible, but you do need to remember some of what you learned about parametrically defined functions. Okay, in order to do line integrals, you're going to have to remember what you learned about parametrically defined functions. That's very important because otherwise you won't be able to figure out line integrals. All right, so that's going to have to be for a separate video, guys, because I'm getting a little tired here. So hopefully this was a good video for you. I hope you learned a lot. I hope you learned a lot of calculus. I hope you learned a lot of Mathematica. And good luck with your studies, okay?